Welcome to day 16 of 30 days of machine learning. Woo, very information heavy past 15 days, and it is only going to continue to get heavier because it is from today that I am very excited to announce we are finally stepping into deep learning territory. Okay, so from today, the models are going to go towards deep learning. So, quick introduction from till now. Whatever models we have built predominantly, they have been classical traditional machine learning models. Okay. So now we are going to start with deep learning, and the primary difference between the two. So machine learning basically is comparatively very naive, very simple compared to what deep learning can do. Deep learning is basically the idea about deep learning is based from how the human brain thinks. Not exactly, but it has tried to replicate the thinking of the human brain, and from there on, it has gotten on to advanced. Okay, so we are going to start with the most simple of deep learning problems, and then slowly go towards all that we can cover, eventually going towards transformer models as well. Okay, this is probably by far the most important video in the series because this is going to form your intuition for all of the deep learning content that we are going to cover after this. So pay attention. Now, without wasting any time, let's step into the problem today. What do we have on our hands today? So you can read the repo alongside, like I always suggest, and there are going to be two or maybe even more articles in the description for you to read. Okay, whenever these things feel overwhelming, whenever they feel like there's too much information to understand or capture in your mind at once, I always recommend reading. Study it once, revise it, read it again, and at the same time try and memorize it. Okay, so let's go on. So today on our problems we have an MNIST image classification problem. Okay, so the MNIST dataset, I think this is not the first time we are dealing with it. So it is the bread and butter dataset available for machine learning and deep learning problems. So this dataset has a collection of 60,000 handwritten images from 0 to 9. Let me quickly show it to you on the board so that we can make things comparatively clear. So let's say this is a 0, this is a 1, 2, 3, okay, all the way up to 9. In this data set we have got images of these numbers. So this is one image of 0, then this is of 1, this is of 2. So like this, all the way from 0 to 9 we have different images. And how many images are there? 60,000 of these images in a total. So it is a massive data set compared to what we are doing. And the problem is saying that at random, the tester, or in the training, after the training, in the testing or in the validation part, someone is going to say that, okay, I have this image right here, and your machine learning model or your deep learning model, whatever you can call it, your AI model, when I take this image of 3, and I give this as input inside your model, it should be able to predict correctly whether this is a 3 or not, or whether it is some other number. Okay, so our task is basically like a multi-class classification problem. Okay, so till now we have done many problems of binary classification. So binary means 2, which means either 0 or 1 kind of problems. So we have done spam, not spam classification using naive Bayes, I think on day 6. We have done customer churn. Okay, so we have covered a lot of binary classification problems. Today on our hands, we have this for the first time in the series. We have got a multi-class classification problem. Okay, simple till now, right? Multi-class means there are multiple classes. So we have got a total of 10 classes here. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 10 classes in total, and our task is that whenever a number is given to us, whenever the image of any of those numbers is given to us, we have to correctly predict its class. Okay, so how can we solve this problem? Let me quickly show the same thing to you in the repo as well before moving forward. So this is it, and see, 10 categories 0 through 9, and all of the images are 28 by 28, which means let me open up the image for you so that it becomes visually clearer. Let's say this is an image of the number 5, and this is how the image is looking like. So as we know, every image in the world has pixels. So this is basically a 28 by 28 image. So 28 pixels for the height and 28 pixels for the breadth or the width, which makes it like a total of 28 multiplied by 28, which means nothing but 784 pixels. Okay. So I think I've mentioned this before as well, but I will say this again because it is very, very naive and basic to understand. So, the machine learning model or whatever model we are training, it does not care about 28 by 28 or 2 by 2 or whatever. For the machine learning model, only this number 784 exists. Because we cannot take 28 into 28 and feed it into a model. What we will be feeding into the model for training will be the number 784, like a 1D image. Okay. So this image right here, this is a 2D image. But we cannot feed the 2D image directly. We are going to feed the 1D vector of this same image. So 784 pixels are what, like a 784 length vector or like a 784 length array, 1D array is what we are going to feed into the model for training. Okay. Now, this is something very simple. So images usually in machine learning models, they can be of two types. They can either be colored or they can be black and white. Okay. So the colored images are called as the RGB images, red, green, blue images. Okay. RGB here are three colors, and in machine learning terminology, these are called as channels. So we can say that there are three channels in RGB images. Okay. And our dataset today, the MNIST dataset, it is a grayscale image dataset. So let me write here grayscale. Grayscale means only white and black images. Okay. So grayscale has only one channel. Okay. Not two, only one channel. Okay. So what happens in a grayscale image is that you can either have black or you can have white. Okay. So these grayscale images, they are basically 8-bit images. Okay. 8-bit images, and the pixels inside the images can have any value between 0 to 2 to the power of 8. Okay. If the pixel is 0, exactly 0, it means that the color of that pixel is going to be black. If it is 255, it means that the color of that pixel is going to be white. Okay. And any value between 0 and 255, it means that the color of that pixel will be some shade of gray, some shade of a mixture of black and white, which is why it is called as a grayscale image. Okay. And it is 8-bit because 2 to the power 8 comes out to be 256, and 256 minus 1 is 255, which is exactly what we take as the range of pixels. Okay. So this is very important because in the model that we are going to discuss and build today, we are going to deal with these pixels. So it is very important that you get this concept inside, that we are going to be talking in pixels a lot of the time. Okay. So 0 to 255. So let me give you an idea again quickly how the data set is going to look like. So we have got 784 pixels. Okay. And all of the 784 pixels are going to have some value between 0 and 255. So for example, if some pixel of the image is completely black, then it will have this value 0. If some of it is having some shade of black and white, gray, it is going to have this value. If it is completely white, it will be 255. Okay, then some other number, then some other number, and this way it will be a length of 784 pixels, all having different values between 0 and 255. Okay, so let me show you what an image of this dataset looks like so that what we just discussed becomes a bit more clear. So this is an example of how the images in this dataset looks like. See, all the numbers are there, and only the information inside the image, which means the number that we are looking for, is only somewhere in the middle. Rest of the way it is completely black. So wherever we are seeing completely black, it is straight away going to be a 0 value. Okay. So this is important to discuss. We have got 10 classes because numbers are from 0 to 9. And this is our training images, 60,000 images. I'll tell you about that later. Okay. Now, the main question that comes along, since we have understood the data set and the problem, let's start solving it. How would we approach such a problem? Okay. Like if I asked you, you have got 10 different classes and you need to classify images. So you got it that it is a multi-class classification problem. But how will you approach it? So for the first direction to think will be in the direction of a traditional machine learning model, of course, right? So maybe we will try SVM, some SVM kernel. So SVM basically tries to exploit the geometry between different classes and to draw different lines between them to find the perfect hyperplane, and based on that we can classify. Maybe we can try that. Maybe we can try some variation of random forest or decision tree. And the thing is that all of these approaches are all right, but they will only work till a certain extent. And there is a reason for that. Okay, which brings us to the primary disadvantage that traditional machine learning models carry. So let me explain this to you using a wonderful example. So let us take this number 3 right here. Let's say that this is our input image which we are trying to predict. Now, when I ask you what is inside this image, what will you say? You will say it's a 3. But I ask you, what makes this number a 3? Right? It is a stupid question. I can identify this is a 3, you can identify this is a 3. But if I ask you what makes this number a 3, you cannot give a definite answer, right? Because you have just memorized it. We are all humans. We process data and matter in a certain way. We just memorize it that, yeah, this is a 3, it has got this loop and this loop. But now we are talking in the context of machines. How will a machine learning model, or how will a machine in general identify that this is a 3? How can it do it? So the machine will maybe think that, yeah, this pixel here is dark, this pixel here is not dark, and there is this loop. So maybe based on that it will try and say that, yeah, this is a 3 based on uh, the pixel geometry, right? Maybe we can say that. But the thing is, we cannot really answer this with a single rule. Why cannot we answer this? Because what makes this a 3 is not one pixel. Okay, it is not one pixel that makes this image a 3. It is the interaction of thousands of pixels inside. So now what happens is that when I give you this 3, when I give you this digit 3, it is not because the 3 is 3, not because of one pixel, but because of the interaction of many pixels inside this image of 3. That is what exactly makes it a 3. Okay. So, the point of this is that we cannot try and linearly define how a 3 image is a 3 image. Okay, we need to cover a lot of the complex patterns inside this image in order to really deeply identify what differentiates a 3 with something else. Because let me try and make a 3 right here. Okay, and this is the image of 3, and let me now try and make the image of 8. Okay, so now these two images, they are confused a lot whenever we are trying to build image classification models, because the difference is that I can say that this is a 3 and this is a 8, but what the machine sees is that when I write a 3, the only difference between a 3 and a 8 is these two loops right here. See, if I add this loop right here, I can convert a 3 to a 8. Okay, so the machine cannot differentiate between the image of a 3 and a 8 like we can. It relies on looking at how the stroke geometry is, like how the angles are made, how the loops are made. Okay, and this way it tries to really get through it. Now the traditional machine learning models that we usually deal with, they cannot identify these complex features. They try to make everything very simple, very additive, like a linear model. So for example, if I use some naive machine learning model to solve this problem, it will say, okay, this pixel is you know this pixel is not this pixel is dark, it has no value, so maybe we can give it a 0. This pixel has some value, so we give it some sort of pixel value. This has a loop, so we give it a value. Okay, 3 and 8 both have loops, so they are close to each other, but in reality they are not close to each other. They are completely separate images, but the naive model cannot understand this very well. Okay, so that is the problem here. Real world handwriting is based on a lot of complicated features. It is not linear at all. But our naive models try to fit it in the direction of some sort of a linear model. This is why in the task of multi-class classification, specifically for images, the traditional machine learning models fail, even the strongest ones of them. Okay, because they cannot handle these complex features. Okay, because see, let's take another example to clarify it. You can take the example of this number 4. Now some people make 4 like this, some people also write a 4 like this. Now look at how this 4 and this 9 look so similar to each other. Okay, the only difference is that 9 has a loop here and 4 has a straight line here. Now the naive model would consider them to be almost the same numbers. It cannot differentiate between the complicated patterns right here. So for that we need a separate approach. We need a different approach to go through with this. So what approach is that? How to deal with it? What approach is that going to be? So the thing is that the idea here to get the correct model is that rather than thinking about a single feature, rather than thinking in the terms of linearity, we think in the terms of mathematics. Maybe we can have small mathematical identifiers that can really differentiate in the features between these two images. Okay, so let's say we have got identifier 1. Okay, like a mathematical feature identifier, this can identify the loops in the images. Okay, we have got identifier 2, which can identify the stroke geometry, how thick a written stroke is or how thin it is, so it can identify the stroke geometry. Okay, then we have another one which can identify the color or the pixel intensity in the specific image. Okay, and this way we can have we can have millions of small mathematical identifiers, small mathematical functions which can give us some information about the image that we need to differentiate between them. And then for the final result we can compile or we can concatenate all of those mathematical identifiers and give an output. So will this approach work? So let's check it out. The answer is yes, that this approach will work, but let's check it out how. Okay, so let me show it to you how it works. So the idea, let me write it down first. The idea is to stack multiple models to identify different features in data. Okay, so this is the idea here. So the thing is, instead of manually telling the machine, instead of manually telling the computer that what a 3 looks like or what a 5 looks like, instead of manually coding it that that is a 3 or that is a loop, that is a straight line, we rely on millions of small mathematical units which will learn these rules themselves. Okay, so this idea of using millions of small mathematical identifiers that can learn the pattern themselves. This idea is basically called as a neural network. Okay, so a neural network is basically the beginning of deep learning. It is the first deep learning network ever made. Okay, no need to get overwhelmed. It's just a big word. It is rather easy to understand. It's pretty easy to interpret actually. So a neural network is a deep learning model which basically works according to similar to the principles of the brain. So if you have studied about 8th or 10th grade biology, you know that a neuron is basically like a small cell inside the nervous system, inside the brain. Okay, so this neural network also has thousands of these neurons. Like we discussed here, that the idea here is to stack multiple or millions of small mathematical units. So the neurons here function as those mathematical units which will help us to identify all the features inside the data. Okay, so the neural network works on the principle of the human brain, but biologically it is not the same. This is a common misconception. Neural networks are not based on the brain. They are similar to how the brain processes signals. Okay, So the signal processing ability between the neural network in a deep learning model and the neural network or the neuron in our brain is similar. That is the only thing that you need to remember. Okay. Now, let me show you how we move forward with this. How does, a neural network architecture looks like and why it is so strong. So, first of all, let's talk about a single neuron. What does it look like? So, let me go back to the original problem that we had. So, what was the problem that we were having? We basically had 784 pixels that we were dealing with, right? 784 pixels. So maybe we can write them like x1, x2, x3, okay, all the way up to x784, okay, meaning that there are a total of 784 pixels which are carrying some input data. Every pixel is carrying some data, okay. Now what is our job? What is our job that we want to do with this neuron, with this neural network? What we want is that we want neuron to come and really go inside these pixels and to extract different information from them, okay. So maybe we can take that, maybe we can try that. So the thing is, whenever we are trying to talk about a neuron, we talk in the term of weights, okay. Each neuron has a weight, basically a value, which is which is different for different neurons, which helps it to extract information from the input data. So let's talk about neurons. So we can have a single neuron or we can have multiple neurons inside our neural network. Usually we don't use a single neuron, we try and use multiple neurons so that we can identify multiple patterns and multiple complex features inside the input data set. So let's say that the first neuron is called as a W1, then a W2, okay. And the number of neurons that we are choosing in our neural network can be decided by us. It basically depends on the complexity of the problem, okay. So usually neurons are taken in the multiple of 32 usually. So you can choose 32, 64, okay, 128, 256. You can choose less as well, you can choose some value between them as well, but these values are very very uh, preferable because they go very well with the GPU parallel programming, any multiple of 32 basically. So let's say we have got 64 neurons in this case, in our case currently. So these neurons are going to go like this, okay, and each of them has a separate weight. Initially that weight value is a random number and then it is learned during the network later, okay. So how does it move like? Let me show you how does it move like with a diagram. So this is our input x1, x2, x3, all the way up to x784. Now what is going to happen is that this is the input layer of the neural network, okay. This is the input. Simple, right? Okay. Now we have the neurons. So we have the neurons right here. We have got W1, W2, W3, we have got W4, all the way up to 64. Now what's going to happen is all of these neurons are going to interact with these inputs in order to extract different information about the features. So like I said that since it is a handwriting based data set, there are lots of complicated features. Stroke geometry, okay, pixel intensity, color, then angles, all of these different features. So these 64 neurons will extract all of these information from different pixels at once, okay. So this basically forms part of a fully connected network. Basically this x1 will interact with w1, okay, it will interact with w2, w3, w4, it will interact with all 64 of them, okay. This first neuron will try for the geometry part. It will search for the geometry inside x1 pixel. This one will go for maybe the stroke pattern, okay. This will go and identify the loops, okay. This will go and identify the pixel intensity, okay. And similarly, all 64 will have different functions, and they will identify all of these important features that we are trying to search from the pixel x1. Similarly, all 64 neurons will interact with this pixel x2. Okay, all 64 of these neurons will interact with this pixel x3. Okay, so you see how everything is getting connected with everything. This is called as a fully connected layer or a fully connected neural network. Okay, in the code I will explain this to you as well. This is a very important term. This is called as a fully connected layer. Okay, because see, everything is getting connected with everything. Okay, this is very important. This is, going to build your intuition for a neural network till the end. So try to understand it very, very carefully. First of all, we have got the input. Why 784? Because we have a 28 by 28 pixel image. And of course, like I said, the machine does not care about 28 or anything else. It tries to condense everything. It tries to, bring everything in a 1D form, in an array form. And what will that array length be? 28 multiplied by 28, which gives us this 784 number. So this is nothing but a 784 length array. Okay, and this will contain information about all of the pixels. Okay, now to extract the information about the pixels, like I said, we will use tiny mathematical operators. What we are saying is, all of these tiny mathematical operators, we'll say go to pixel 1 and see what you can find. Okay, are you done? Then go to pixel 2 and find. Go to pixel 3, and this way for all 784 pixels. And since one neuron is not enough, because we are not searching for one feature, we are searching for geometry, stroke, loops, pixel index, color, shape, angles. We are searching for so many different features, which is why we need many neurons in this case. In this case, we have chosen 64. You can choose any number around about as well, but 64 proved to be enough for this problem. Okay, so this is basically part of the input layer of the neural network. Okay, so now alongside we'll quickly write the math for it. So the math is very simple. So I showed you these interactions, right? X1 is interacting with W1, W2, W3, W4. How does it look like in mathematical terms? So in mathematical terms, this is represented using something called as the weighted sum. Okay, and the weighted sum looks nothing but like the summation of xi, which means the input, and wi. Okay, and I goes from 0 to whatever the input length is, that is 784. Okay, and this other I, maybe we can write j here to avoid confusion. So this j also goes from 1 to all the way to 64. Why 64? Because we have chosen 64 different neurons in this case. Sorry, this will be 1. Okay, this is what the weighted sum looks like. Now the thing is, sometimes this xi value can be 0. Can it be 0? Yes, it can be 0. If the pixel is completely black, then this value will be 0. Now if xi becomes 0, then this multiplication will also become 0. So to prevent the weighted sum from becoming 0, we also add a bias term called as b. Okay, so b here, the bias term is nothing but it is just a small value to prevent this sum from going to 0. Because if it is 0, then our model will not learn anything now. We wanted to learn something, anything, like a default value. So this bias prevents that. Okay, it can be any small positive or negative number that we add. And it is not usually chosen by us that you can take 5 as the bias or 2.3 as the bias. It is assigned during training itself. Okay, so this is the mathematical operation that happens in the first layer. Okay, it basically gives us an interaction between all of the neurons and all of the input added with the bias. Okay, now very important thing, let me change the color. Yeah, so look at this very carefully, this equation that we have right here. What is it looking like? Is this equation making some sense? Now it is making sense, but the thing is, if you look at it carefully enough, this equation still looks like a linear equation, right? Yeah, we have taken different mathematical units and we have tried to multiply them with the input so that it can learn something, but this is still very linear. There is no operation inside it to capture the features that we want to capture. So how do we change that? How do we introduce some non-linearity into the model? How do we, allow the model to learn some non-linearity? So that brings us to the second layer in the neural network, which is called as the hidden layer. It is the most important layer in the neural network because it is actually finally something new. This weighted sum and feature interaction, basically, we have done things similar to this before as well. The hidden layer is going to be completely new. So let me show you what is happening inside the hidden layer. Okay. So the hidden layer is basically responsible for introducing non-linearity inside the neural network. So, let's say we have got a group of detectives. Okay. There are junior detectives who go and find all the clues inside the case, whatever is happening. They go and, investigate the bodies, they talk to people, they identify clues, they pack evidence, and then comes the senior detective. The senior detective tries to combine all of the stuff that the juniors have given in order to, really give meaningful insights about the data that they have collected. So you can take this analogy and apply it to our case. So the input layer does the work of the junior detective, where it is basically, doing the feature interactions, adding the bias and all that. And the hidden layer will be the one to introduce the main thing into the model. So the hidden layer has a very important concept called as the activation function. It is something that is going to be used in the entirety of deep learning, and it is even used in transformer models and even in the models that we use in our daily lives. Chat GPT, Claude, all of them make use of activation functions deeply. So an activation function is basically some mathematical function which whose function is to introduce non-linearity into the model. So there are many kinds of activation functions, but the one that we are going to use today is called as the ReLU activation function. Okay, ReLU. The full form is nothing but rectified linear unit. Okay. So how does ReLU look like? What happens when we give ReLU some value? So let's say that F is the symbol for ReLU, and if I give some input value X inside of it, it outputs the maximum of 0 and X. Okay, so I'll try to uh, explain this in a good manner. So let's say that the input inside ReLU is -1. Okay, so it is going to the output, when I put this plug in this -1 inside the function, the output is going to be the maximum of 0 and -1. Now what is the maximum of 0 and -1? It is going to be 0 itself. So this is like a property of the ReLU. It is an advantage and a disadvantage both in some cases, that ReLU does not output any negative values. You see, because the maximum value between 0 and some negative number is always going to be 0, because 0 is greater than -1 na. 0 is also greater than -99 or -99,000. So any negative value of X, and the output for ReLU is always going to be 0. And if there is any positive number, then the output is going to be that positive number, because let's say that my X value was 25. Now what is maximum of 0 and 25? 25 itself. So this is a good property of ReLU, that it avoids all negative numbers. Okay, and it basically gives us these outputs, and there will be no negative numbers in our training. So this is used to introduce non-linearity into our neural network. Without an activation function, our neural network is similar to a large linear equation. Okay, it is basically useless without an activation function. An activation function is what actually powers a neural network through. Okay, now let me go on to the next thing that we have to discuss. Okay, so after we have applied ReLU, what happens in the network is, so we had these weighted sums. So let me write it down. This weighted sum formula, it is represented by the letter Z. Okay, so this is how it is written like. This is how we write it. Okay, this is called as Z, and here we write Z input, which means that this weighted sum came from the input layer. Now we have got these weighted sums, and we have got the weighted sums for all of them, basically for all of these 784 neurons. Now we pass them through the ReLU layer, okay, and the ReLU is a part of the hidden layer. So we had the input layer right here, and we had the hidden layer right here. Okay, so in the input we had these interactions between all 784 features like this. Okay, here we had the neurons, all of them, all 64 neurons. Okay, so this interacted with this, all of them interacted with each other to produce our final weighted sum. Okay, like this. So this makes it a fully connected network. Now these outputs, this is basically Z, Z, that is coming from the input layer. These are passed through the ReLU layer in the hidden network. Okay, and the ReLU basically will convert all of the negative values to zero and keep the positive values as it is. This will introduce the non-linearity into the model. So these are going to be sort of the outputs for the ReLU after applying the ReLU. Okay, now, after we have applied the ReLU, we need to produce an output value. Okay, we need to produce scores in order to prove that, yeah, uh, what class does our input image belong to. So we are going to produce the outputs. So the outputs are going to be scores, some scoring values. So whenever we get the output out of the hidden layer, so let me write the equation. So till now we had the equation for the input layer like this. Okay. Then we applied the ReLU and we got the output for ReLU. So we can say the ReLU has been applied to Z, right? Z right here. Now after this A, basically the output that we receive from ReLU is passed through another linear layer like it did right here in order to produce output scores. So again it is produced like this. See, some weights are provided multiplied by A plus B. Okay, I can write Z O here, basically standing for the output for the Z value for the output layer. The weights are going to be different. These are not the same weights as they were used up here. Okay, and this is going to be the output value. So the output value is going to look something like this. So we have 9 classes, 10 classes actually, 5, 6, 7, 8, and 9. Okay, so we have got 10 different classes in here, and the thing is our answer is going to look like this. The outputs are going to be some scores. So for 0, let's say it gives a minus 1.2. For 1, it gives a value of 2. For 2, it gives minus 0.3. Okay, for 3, it gives 3. For 4, it gives minus 2.7. For 5, it gives 1.6. For 6, it is, so we get some values of scores for all of these numbers right here. So let's say for 7 we get some 1 point minus 1.5 value. Okay, for 8 we get some value of 1. For 9 we get some value 0. Okay, the thing is that these scores that we are getting, these all of these values in the output, they are not really interpretable values. We cannot interpret them. See, by looking at this 0 class, I say that the chance that a number can be 0 or 1, so for 0 that answer is minus 1.2. Now how can you form an answer with minus 1.2? It is not an interpretable number. So to convert these raw scores to interpretable numbers, see, these are raw scores or logit values. To convert them to interpretable numbers, we need to apply some mathematical operation. Okay, so uh, what is the mathematical operation that we can apply? The thing is that we have the output, but we need to convert them to maybe probability values, right? So if we have probability values for each class, then we can answer the basic question that what each thing is doing, and basically like an answer for what probability is that each digit looks like 0, 1, 2, or whatever it looks like. Okay, so how do we do that? We do that using a very important concept called as the softmax function. Okay, so let me just select this. Yeah. So we do that using the softmax function. So the softmax function is very important as it is used basically everywhere in machine learning. So the softmax function looks like this. Its job is to give us final probability values from any raw scores that we are dealing with. Okay, this is what the softmax looks like. Okay, so all of these values that we were having in our case, all of these values are passed through softmax. Okay, and the advantage of softmax is that whenever something is passed through e, okay, whenever something is passed through an exponent, the low values go and become lower and the high values become higher. So let's say that in this case we are calculating for the class 0. Okay, so in the case of class 0 we are having a score of minus 1.2. So when I write e to the power minus 1.2, it is going to be a value lower than 1.2 itself. Okay, actually much lower. So all of the values having low weights, having low final scores are penalized, and the higher values are actually rewarded. So let's say for 8 I have got a 1. So e to the power 1 comes out to be 2.7, which is nothing but the value of e itself. So this is how we can interpret the values. And all of these are going to be probability values. Basically, if we add all of them up, the total comes out to be 0. So this pi is calculated for all 10 classes. Okay, it will be calculated for p1 by inputting inside this formula. Okay, this denominator right here, it is nothing but the total of all the values. Okay, so when we apply e to the power minus 1.2, we get the value for class 0. Then we calculate e to the power 2 for class 1, then e to the power minus zero point 0.3, and we add all of them up. So the denominator is nothing but e to the power value of class 0 added to e to the power value of class 1, e to the power value of class 2, all the way up to e to the power value of class 9. So it is the total of all the classes. And in the numerator, we get the value for the specific class. So if it is class 0, then it is going to be the final probability value for class 0. For class 1, we can input in zi, we can input 1, and we can calculate basically e to the power 2. Similarly, we can get probability scores for all of these classes, and whichever class has the highest score is going to be our answer. Okay, so this is how multi-class classification works. Like it works by using the softmax probability function, which is the most important to interpret probabilities. Otherwise we will get scores that we cannot interpret. Okay, so quick 84 inputs on our hand. Okay, we then go on to the next layer where basically we get the weights from the different neurons. Then we calculate the weighted sum and we add to it the bias so that the weighted sum does not become 0 like in some cases. Then we go on to the hidden layer and we apply the activation function to introduce non-linearity into our network. After this, we calculate the raw output scores. You can say raw logits or raw output scores. Okay. And then finally, to make the raw logits interpretable in the form of probabilities, we apply the softmax function in order to get the final probability outputs. Okay. So after the softmax, we get our final answer, the outputs. Okay. This is how the entirety of the network looks like. Okay, so let me quickly show you the diagram so that it becomes absolutely clear. If you come back to the repo, You can check out the diagram. So you can read this. This is the same things that we have been discussing about the data set. Okay. So this is how the network basically looks like. Okay. This is the input layer 784. This is the hidden layer which consists of the neurons. See, sigma wx plus b. This is the same weighted sum that we calculated. Then the ReLU has been applied. This w1 and b1 is basically showing the weights and the biases. And then we finally get the output. This dropout, I will explain it to you later in the code itself. Okay. Now in the output we have got 10 neurons. Why 10 neurons? Because we have 10 classes, 0, 1, 2, 3 all the way up to 9. Then to convert those output values into logical probability scores, we apply the softmax right here, and based on that we decide which class our number belongs to. Okay, so whichever softmax score will be having the highest value is going to be the class that we assign a number to. And see, all of these are connected with each other, which is why this network forms part of a fully connected layer. Okay, so this is how it looks like. You can look at the math here. This is exactly what we discussed. See, this is exactly what happens in the forward pass. The This is the first weighted sum we calculate. Then the output of the ReLU. Then the output of the ReLU is fed into the output layer. This is the output that we get, and we need to convert it to probability scores. So this is it. If you want to read more about the ReLU, it is available here. ReLU and Softmax both. They are very important activation functions, but we are not discussing them in much detail. Okay. So now, like every model that we deal with, we need to understand about how the loss is computed in this model. Okay, what loss function do we use and how do we move forward? So it is a pretty quick process to derive and move forward with the loss function, but it is pretty important. Okay. Okay. Categorical cross entropy. This is exactly what we use moving forward in any neural network with multi-class classification problem. So I think you will remember BCE that we used in some of the earlier videos. BCE is nothing but binary cross entropy. So binary cross entropy is intuitively for two terms. Since we have multiple categories here, we use categorical cross entropy, which is also called as the log entropy. Okay, so it is very logical to use. uh, this is what it looks like. Okay. Okay, and this yi hat is nothing but the predicted values that we have on our hands. This yi is the actual, the calculated values. Okay, this is how it happens. So this is what the log functions look like. So now, like any machine learning model, whenever a model gives out some sort of error, we need to go back and correct it, right? We do that by the process of backpropagation. Basically, all of these training steps that we just discussed in our model, uh, these steps where, you know, we basically start from the beginning, calculate the weighted sum, then the ReLU, and then the outputs. These form the part of the forward pass, basically how the model is trained. Now, after the model is trained, in the first iteration, in the first epoch, there are going to be some errors. So how does the error correction happen? So the error correction happens in the backpropagation. Okay. So let me write it down. Okay. So for the backpropagation, first of all, we calculate what is the error at our output layer. Okay. So if I write it down in the most simplest of terms, this is what our error looks like at the output. This is the predicted value, the calculated value that we had, and this y is the actual value. This is the error at the output layer. Okay. You can write ZO here because Z is used multiple times. So ZO basically means the Z value we had at the output. Okay. Now what is our goal? Our goal is to calculate the derivative of loss with respect to the weights, because whenever error correction happens, we need to go back in the back propagation process and correct these weights, this W value. Okay. our goal is to calculate this del L by del W value, which basically means the derivative of loss with respect to the weights that we are dealing with. So this is nothing new. We have been doing this for a while, and we calculate the loss with respect to the weights because whenever the error correction happens, we cannot change the input. We never go and change the input back. We actually change the weights. Okay, so these weight values, I think I have discussed this before as well. These weight values are learned. Okay, these are not calculated weight values. These values are determined during training, and we need to shift them accordingly. We need to change the values accordingly in order to reduce the loss function to a minimum value so that the accuracy comes out to be at a maximum. That is our goal in all of training. Okay, so uh, this is the prediction error, if you can see it. Okay, this error is the prediction error in the output. Okay, whenever we calculate del L by del W, okay, so we can change and write this like del L by del Z multiplied by del Z by del W. So this is not nothing but the chain rule of differentiation. Okay, so this is very important. The chain rule is what drives or powers all of backpropagation throughout deep learning. So since we cannot directly calculate the derivative of loss with respect to W, we try to do it using the chain rule. Okay, so we have got the value of Z here, the Z at output, which is nothing but the weights at the output multiplied by A plus the bias. So let me quickly show it to you what I am talking about. So since the Z that we are dealing with is the Z at the output layer, so if we go and check out what the Z value was at the output, we can see that in the output the Z was nothing but this value. So the A is the output from ReLU that we calculated right here, and then basically pass it through another linear layer. Okay, so this is inside this. Okay, so when we write del Z naught by del W, we basically want the derivative of Z naught with respect to W. So this W and this B, the B is a constant value, so this cancels off to 0, and the derivative of W naught into A with respect to W is basically A. So this value, okay. So whenever we are dealing, okay, so whenever we are dealing with this value of del Z naught by del W. So we can see easily that when we take the derivative, the B is a constant value. So it is going to get cancelled, and we are only going to be left with this W naught A term. And whenever we take the derivative of W naught with respect to W naught, it comes out to be 1. So only the A is left. So the answer for this value right here is nothing but A. Okay, and whenever we calculate this del L by del Z naught, this is nothing but the prediction error that we had right here. Okay, so the value for the loss with respect to weight comes out to be y hat minus y, okay, multiplied by this value of A. So this is what the loss with respect to the weights comes out to be. Okay, so our standard flow of working here is going to be that we have the output. Okay, we are currently at the output layer, and we have calculated the loss. So here we have calculated the loss. Now after calculating the loss at output, we need to go back to the hidden layer. Okay, why do we go back to the hidden layer? Because we need to trace the position, we need to trace the point where the error was made. Okay, so if we are at the output currently, we need to go back to the hidden layer, and then we need to go back to the input layer. That way we can access the weights that are used during training, and we can basically modify those weights in order to do the error correction that we want to do. So the output is the last step in our training cycle, which is why we cannot go to the output and correct the weight straight away. From the output, we need to go back to the hidden layer, okay, and then basically calculate the loss again, and then finally do the error correction. So we have this value right here that we calculated, the derivative of loss with respect to the weights at the output layer. Okay, so to do the correction at output first, we need to write a formula. So the weights of output are basically shifted according to the error that they were making. This eta is the learning rate, and this loss function is with respect to the output layer. This is how the weight update is happening in the output layer itself. Okay, so if I write it, this is the weight updation at output layer. Okay, now after the weight updation at output, we need to go back to the hidden layer. So now we calculate the derivative of loss with respect to the weights in the hidden layer to propagate backwards. So again, this will be calculated using the chain rule. So we can write something like del L by del Z naught multiplied by del Z naught divided by del W hidden. Basically, the weights at the hidden layer. Okay. So this del L by del Z naught, we just calculated it upwards of here. See, this is basically the prediction error. So we can write it straight away. Instead of this, we can input y cap minus y in here. Okay, so the main thing to solve that remains is this part of the equation. Okay, so del z naught by del w, we can again apply the chain rule in this. So we can write del a, okay, multiplied by del a by del z multiplied by del z divided by del w hid. Okay, so we have applied the chain rule 2 times for this term right here in order to get this. So the chain rule, like I said, is a very prominent method in order to do the back propagation. So this way, we can break the terms down to values that we know and we can get the final answer. So again, this del z naught by del a, this is nothing but the weights that we had at the output. Okay, so if you go and check it out, this z naught value looks like this. Okay, this value, and if I ask you to take the derivative of this with respect to a, so b will get cancelled straight away because b is a constant. Okay, a derivative of a with respect to a will be 1, so only w naught will be left, which is why this term comes out to be w naught or w output, whatever you want to call it. Okay, now this term right here, it will come out to be nothing but x, because this zh is nothing but the first weighted sum that we calculated. So when I write zh, it is nothing but wi xi plus b. Okay, and when I take its derivative with respect to w itself, b will again go off to 0, and the derivative of w with respect to w will be 1, so only x will be remaining, which is why x comes out to be here. Okay, very logical. Now for the last term, this one was a bit complicated, which is why I saved it for the last. The derivative of a with respect to zh. So if you look at a is nothing but when we apply the ReLU activation function to our value of z, and they are asking for the derivative of a with respect to z. So it is going to be nothing but f dash of z, where f is nothing but the ReLU function. Okay, so if we compile it all down and we write it down, so the loss with respect to the weights in the hidden layer come out to be y cap minus y multiplied by w output multiplied by the derivative of ReLU. Okay, and the input of ReLU is nothing but the weighted sum that we calculate multiplied by x. This is what the final equation of loss with respect to the hidden layer weights comes out to be. Okay, so we have got the loss with respect to the output, and we have got the loss with respect to the hidden layer. So this is how the weight updation happens for the output layer. And now since we have this gradient for the hidden layer, we can do the weight updation for the hidden layer as well as part of our second step. So the weights of hidden layer are updated in the same manner. We give it a learning rate and then we give it the value of this gradient that we just calculated above this. Okay. So the main formula for weight updation is this formula right here. You must have seen this a lot of times. This is how it happens in the gradient descent basically. Okay. This eta, this long n is basically the learning rate which decides the step size of how basically how far we go when the loss is calculated. Okay, how far the jump is to either side during error correction. And this long step that we had right here was to calculate this gradient value, loss with respect to the hidden weights. And the thing is, to calculate the loss with respect to the hidden weights, we first need to calculate the output because we are starting from the right side. Let me give you a visual demonstration of this same thing so that it becomes, clearer. So, we start from the input. We move on to the hidden layer where we apply the activation function ReLU. Then we again apply the weighted sum and we get the output. Now when we start error correction, we start at the output and we get our error as something like y cap minus y. This is our first error term. Okay. Then we calculate the gradient of loss with respect to the weights in the output layer. Okay. Why do we do this? Because this gradient is going to be used inside the hidden layer for further calculation. Inside the hidden layer, we try and calculate the derivative of loss with respect to weights in the hidden layer. Okay. We change the weights here using our gradient formula and we use this to calculate this value using the chain rule, and then we finally do the weight updation for the hidden layer. Okay, so basically all of the weights that were being problematic, that were causing an issue, are updated using these two formulas. Okay. Let me show this to you in the repo as well for more clarity. So you can read this. This is for the activation function. So this is the loss function, the categorical cross entropy. Okay, you can read about it as well. This is for multi-class classification. This is how the backpropagation looks like. Okay, see, y dash minus y for the output layer. This is the gradient for the output layer. Then we move backwards to the hidden layer, and this is the weight updation that is happening. Okay, Adam here is nothing but the optimizer that we use. So as we know, we start from gradient descent and then move on to mini batch, then we move on to batch. We have RMS prop. So Adam is the most advanced of the optimizers out there. Its working is basically very mathematically elegant. I have another repo which explains all of the optimizers one by one. You can go and check it out as well. Okay, I'll leave the link. Now the optimizer is done. You can read about Adam here as well. I have left it for you to read. Okay. Now very important, let me tell you two very important concepts which we have kind of avoided here because they are not really causing a problem here, but they might. So these are the problems of vanishing and exploding gradient, one of the most popular problems in all of deep learning. This is the reason why transformers were invented towards the end. Okay. So the thing is that whenever we calculate the gradients like we did here, so you see in this case we are calculating the gradients. So you see when we were calculating the gradient of loss with respect to the hidden layer, how many steps did it take? First of all, we had to apply the chain rule here. Then we had to apply the chain rule again here. See, this is again we had to apply the chain rule 2 times here and then 1 time here. Now the thing is, these are derivatives we are talking about with respect to weights. These are very small values, okay? And the thing is, when this is repeated for a lot of steps, okay, the final value comes out to be very small. Let me show it to you. Let's say I'm calculating the gradient like this, okay, and I'm applying the chain rule one by one. So I'm going layer by layer. This is my output. Then this is like this, okay, and like this I'm moving backwards. Okay, like this I'm moving backwards until my loss value slowly degrades. So this value is going to be some very small value, maybe let's say zero point 0.1. This is going to be even smaller, 0.01. This is going to be another small value, 0.001. So when these multiple small values are multiplied with each other millions of times, it outputs an even smaller value. Okay. Due to that, what happens is that this final gradient, which is used in error correction, comes out to be a very small value itself. Okay. So we need this gradient value to perform some changes so that we can shift the weights in order to reduce the loss and to increase the accuracy. But if this loss value is very less in itself, we are not really making any changes, right? We need this to have some significant value. If it is having some very small insignificant value like this, then what is the point of training? So the gradient for the loss, when lots of small mathematical steps are involved, the gradient almost vanishes. This is called as the problem of vanishing gradient. Okay, very small values basically multiply with each other and form an even smaller value. So you can read it here as well. Okay, you see the gradients, they shrink exponentially with depth. Okay, and by the time it reaches the early layers, it is close to zero, so the layers actually are not performing any real learning. Okay. Now we have prevented this problem here because we use the ReLU activation function. Okay. So the thing is, the ReLU, since it has its values between 0 and x, which means 0 and any positive number, the derivative of ReLU is 1 whenever the neuron is active or present. It is never a fraction. So this is the advantage of using the ReLU activation function. It never leads to the vanishing gradient problem. In fact, like for a few layers it won't. If you are building a very deep neural network, it might still cause problems in the later layers, but for this problem it is never going to cause an issue, the vanishing gradient. Okay. But there is also slight disadvantage that comes with the ReLU. So the thing is, since the ReLU outputs only positive values, so when I write this, now imagine that some negative value was an input inside the ReLU. Let's say x is equal to minus 2.3 was the input inside the ReLU. Now the ReLU is never going to output minus 2.3. Its output is going to be 0. But the thing is, this minus 2.3 still has to contribute to training, right? This minus 2.3 is still a significant value that is contributing to training. But our ReLU function is automatically cancelling that, is automatically making that equal to 0. Now this way what happens is that some of the neurons which were carrying negative values are never used in training, right? Because any negative value, the ReLU is automatically going to convert it to 0. So there is no point of having that negative value, right? There is no point of carrying these values around if they are automatically cancelled off to 0. This leads to another problem that the ReLU brings, which is called as the dead neuron problem. Basically, the first few neurons which give off negative values, they do not bring any meaningful output to our model. Okay, so those neurons are basically dead in the training. This is called as the dead neuron problem. It is exclusive only and only to the ReLU activation function. It does not happen in any activation function. Okay. Uh, this is the optimizer. You can read about it. Now, very important. Let me first show you how this is happening. So this is an important step. We'll discuss this in the code itself. So, like I told you that the pixel intensities in this case are going to lie between 0 and 255. So some pixels may dominate the data, right? Because larger weights automatically dominate the data. So we need to bring them all to a comparable range. So we divide them by 255 so that they can be brought to a comparable range, basically between 0 and 1. So this is very important. We have been doing this for a lot of time, basic normalization or standardization, okay, as part of the data pre-processing. Now let me quickly open the code, check out the code. So the code here is completely new, which is why we are going to discuss it slowly. We are going to discuss it end to end. I'm going to try and cover everything regarding the code, okay. So the code here is built using the PyTorch library, okay. TensorFlow, I don't think I have used much of TensorFlow in any of our models. PyTorch is faster, it is compatible with CUDA, and the knowledge graph it builds the knowledge graph about our data and our variables on the fly. So it is super fast and super optimized to work on any deep learning problem. Okay. So import torch, this is how we import our model. Okay. Torch.optim is used to import the optimizers that we are going to be using. Now the reason why the PyTorch library is super optimized for neural networks is because it contains the classes of neural networks. Okay, it has pre-built classes about neural networks, so it has a lot of pre-written code that we can export and use. Time library, this we use to calculate the inference latency, the training time, and Seaborn and Matplotlib are common for the visualization. Okay. Torch Vision is another library that we use for our datasets, and Transforms is used in order to compile our pre-processing steps. This data loader, it's again a new thing. It is part of the PyTorch library itself. Okay. So it is basically a utility function that is used to load data into our models. So the thing about PyTorch is that it converts its data into something called as tensors. So you have heard about vectors definitely. So let me show it to you. So basically what we have on our hands is 60,000 different images in our training data. Okay. And they are grayscale images. Now, like I said, grayscale images have one channel inside of them. RGB images have three channels, grayscale images have one channel. What is the length of each image? 28. And what is the width of each image? 28. Okay. Do you see this 3D vector right here having three values? Okay. This is basically called as a tensor. This is the kind of input that we supply inside the PyTorch code. This means the channels, this is the length or the height you can say, and this is the width. This is the input format that goes inside PyTorch whenever we are trying to train our models. Okay, and these are the total input, basically the 60,000 images that we were dealing with. So this is what we are doing. This is how we import the raw train data. Okay, this line right here, transforms.toTensor, will convert our data to the tensor form that we want. Okay, you can look at the EDA as well. The EDA was very simple here. We basically check for class distribution. So you can see we have checked out the class distribution. First of all, we try and output these images to look at how they look like, and this is the class distribution. So it is near about equal. This is for one, I think. So one has the most images in the data set. Anywhere, I think it's above 6500. Rest, it is a well balanced data set. Okay. So no resampling or class weighting is required. This is how we plot it off. Now, the data pre-processing part. This is the important part. Look at it very carefully. Okay. So the data loader, I told you, it is a part of the PyTorch library itself. It is used to load the data into our model. Okay. Raw train data is what we had before, and this is the batch size. So the batch size helps us to decide how many data points or how much data out of our total data we are going to be using for the training. So it is not always 60,000, but we took the batch size as 60,000 itself because we had to calculate the mean and standard deviation in this case. Okay. Shuffle is equal to false basically keeps the original order of the data so that we can calculate the mean and standard deviation. Okay. Data is equal to next iter loader. So this loader is basically going to contain the data that we were talking about. Okay. 60,000 images, one channel, 28 length and 28 width. This is the format. And whenever we write this 0, this is basically for the indexing. So this is accessing these 60,000 images as part of the first index. And this iter is basically going to iterate in all of the 60,000 images one by one. Okay. So look at it again very carefully. Data is accessing what? All 60,000 images. How is it accessing 60,000 images? Because this loader has 60,000 images in the first index, which is why we write this 0 inside the bracket here. And this iter is something like a for loop, like when we write for I is equals to 0 to n. So to iterate in all the images one by one. Okay. Then we calculate the mean and standard deviation for the normalization that I showed to you in the repo. Okay. Now a new thing, transforms dot compose. So this compose is basically another very useful tool. It basically chains multiple pre-processing steps together. So you see how we use this compose and we convert our data to tensors. We apply the normalization both in one step. So this is how you normalize the data according to the mean and standard deviation, and at the same time convert or input data to tensors. Okay, so you don't need to write both of them separately, because dot compose allows you to do both of these operations in one by chaining them together. Okay, this is how you load the data. So this data is not an external data set. Like in sklearn we had a lot of inbuilt data sets, so in torch as well we get a lot of inbuilt data. So this is how you get the inbuilt data. Okay, now our data here has a 90-10 training split. So you can see 90% of the data has been taken in the training size. This is the validation size. Okay, and this is again the train loader, basically used to load the training data. Okay, now you see when we do the actual training, our batch size is not exactly 60,000, it is 64, which means that we take any random subset of 64 images out of 60,000 to train in the first epoch, then 64 different images again, then 64 different images again, and this is how we proceed forward. Shuffle is equal to true is going to change the order of the images, so that there is no bias present in the training, and we take a different subset of the data all the time. Okay, this is again the data loader to call our data. Okay, now super important, pay attention, this is the most important part in the code. Okay, this is new, and this is why what makes PyTorch very strong in the use. Okay, so the thing is, the PyTorch has an inbuilt module, this nn dot module that I'm talking about. This is basically inbuilt. See, let me show it to you. We imported this nn dot module up here, this. Okay, so this NN stands for neural network that we have built today. It is inbuilt from the PyTorch, and what it does is it has a lot of pre-written code that we can access in order to build our model. We don't have to write anything from scratch. Okay, so we make our own class ANN. So what we build today is called as an artificial neural network, basically like an artificial reconstruction of the neural network inside the brain, which is why it is called as an ANN. Okay, and we define inside it nn dot module. So this is basically like an object oriented programming concept. It basically means that a child class is ANN, and it is inheriting the attributes from the parent class nn dot module. Okay, this def in itself basically creates a constructor so that we can access all of the class objects. Okay, this super method, again, this is exclusive to Python. So what happens is that, like I said, that this class ANN is a child class, and we are inheriting the attributes of the parent into the child. So the thing is, we cannot straight away get the attributes of the child class without first of all initializing the parent class. So to initialize the parent class first, this super init is used. It initializes the attributes of the parent class first, so that after that we can use the child class next. Okay, so we move forward. Self.fc1. So like I said, the layers that we are building, it is called as the fully connected layer, right? You remember? Let me show it to you. In the diagram that we made before, it was pretty early in the video. See this layer that we make, and then all of this is connected with the hidden layer as well. So this is called as the fully connected layer that we were trying to make. So this is exactly what we write in the code. FC1 means fully connected layer 1. Okay, and 784 is the number of the input, and 128 is the number of neurons we give inside of it. Okay, so input and neurons. Then we apply the ReLU, simple as that. The dropout is applied. So about the dropout, this dropout is basically like a regularization technique that we use. So like in the traditional machine learning, we had L1 and L2 regularization along with elastic net. Here we have the dropout technique. So what it does is 0.2 basically means that 20%. So in the training, the model will randomly drop 20% out of all the neurons randomly in the training, so that some neurons are dead always in training. This basically ensures that there is no bias and the results are verifiable. Okay, If we use all the neurons, it is fine as well. This basically helps us to get even more correct outputs. Then we apply the fully connected layer 2. So let me show it to you so that you have no confusion. This fully connected layer is applied here after the hidden layer. This is what I'm talking about. This one right here. Okay. And inside it we give only 10 neurons because we have got 0, 1, 2, 3. We have got 10 classes. Okay. So again back to the code. You can see that 128 is the input in this fully connected layer 2 and 10 is the output that we want. Okay, the neurons. This is the forward pass of the training, basically how it is applied. So since we have defined this constructor using the self method here, now we use it in the forward pass. So we have made the function for the forward pass and we applied basically on this input x. So this is very important to understand. till here till here we have not given any data inside the model. Basically def in itself is basically something that provides the structure for the entire code, the structure for the neural network. We have not provided any input inside of it. Okay, where do we give the input? We give the input whenever we need. So the thing is that you can define it and you can use it anywhere. This is the beauty of using PyTorch. It allows us to do this. So the thing is that when we will build more complicated models, neural networks in the coming days, you will see that you can use a lot of things. So once you have defined this FC1, it can be used anywhere in the entire code in more layers as well. Okay. So this is the def forward. So this is basically the forward pass of training that we were doing during the code. So this is in the forward pass. The forward pass is basically all of these three steps that we do, and the backward pass is the error correction using the gradient descent or whatever you have applied that we have done here. You know how we predict the errors and everything. Now back to the code. So in this forward pass, this X is being given as the input. Then the ReLU, dropout and fully connected layers have been applied accordingly. Okay. This is the training. This is how you initialize the training. So model is equal to ANN. We are basically calling our ANN class to work. What is the criteria for the loss? It is nothing but the categorical cross entropy, which we can use from the NN module itself. So the categorical cross entropy, you see, we have not imported it anywhere because like I said, this torch.nn provides us with a lot of inbuilt code that we can use. So we have directly used it from this nn dot cross entropy loss. Okay. This is how you apply the optimizer step. Okay. Adam is the optimizer that we have used today. Adam is way too complicated to discuss in this video itself, but it is the strongest optimizer till now. You can check out the repo for optimizers to read about Adam and its intuition. This is the learning rate we chose. Again, learning rate can be a hyperparameter. You can choose different values. This was a simpler problem, so learning rate is fine. Okay. Now we record all of our metrics using the training time. 10 epochs have been chosen. So one forward pass and one backward pass make one epoch. So we have chosen 10 such epochs. Okay. So I'll tell you how basically this works like and why, you know, every deep learning model is basically like a very heavy model. So we'll discuss this in a second. This is how you initialize the training. Okay. Uh, Now whenever we calculate the gradients for one for one back, एक second. Now, whenever we calculate the gradients for one backward pass, when we go on to the next step, we need fresh gradients. So we need the value of the gradients that we calculated before to go on to zero so that, you know, we don't carry it forward. So this optimizer.zeroGrad converts the previously calculated values of gradients to zero, so that when we calculate the fresh gradients for the next step, they don't add to the previous values. So this is an important step. Loss.backward is the keyword to initialize the backpropagation process that we discussed, and optimizer.step applies the optimizer Adam, basically this step right here, to our model. Okay. Then the epoch loss is added. So this is something interesting you can try out. Basically you can print the loss per epoch, basically how the loss is decreasing per epoch, how your training step is happening. Okay. Now very important, let me show it to you. You know how I showed it to you that in the Softmax we need final values. So when the raw scores are converted to interpretable values using the softmax, we get some values, right? We get let's say some scores between 0 and 1. But how do we decide what is the output? We basically take the maximum of all of these and we take that to be the final answer. So to take the maximum out of all of these, we apply this torch.argmax here. What it does is it converts, it takes the maximum value from all of the outputs and it chooses that as the answer class. Basically answering that the image, the number given in the input image is a 3 or an 8 based on the maximum value. Okay. This is how we record the correction, total size. Loss.append, basically we are adding the epoch loss to this losses array that we make. So this losses array was initially empty. Now we add stuff to it. Okay. Uh, this is all same for the training. You calculate the validation, accuracy, the loss. Okay. This is how you print the loss per epoch, training time. This is all old. This is all basic, by the way. Inference latency, okay, this we have discussed. Yeah, confusion matrix. So now till now we have built confusion matrix only for binary problems. This confusion matrix will be a 10 by 10 matrix because we have got 9 labels in this case, from 0 to 9, 10 labels basically. We plot a heat map for this. A naught is equal to true gives us numbers inside the heat map. FMT is equal to D basically takes out the trailing decimals inside it, and we plot it out. So now the very interesting thing, the output. So you see how we are getting this loss per epoch. We have got 10 epochs from 0 to 9. Okay, see how the loss value is reduced from 258 all the way to 43. Okay, and look at the accuracy increasing. It increased from 90% to 98%. A little more epochs and maybe the accuracy goes on to 99 or even 100%, but this is a totally acceptable value. Precision recall, F1 score and support, typical. This is how the confusion matrix is going to look like. Okay. See this, let me open this up in full screen. See, this is the confusion matrix. So it is like a 9 by 9 matrix, predicted and actual values. So these blue values are the true positive values. Okay, you can look at them. So I think can interpret them later. This is easy. These are basically the curves for loss and accuracy. Simple. Okay, so I think this was it for the code, and the code is very important, and what I suggest is that you can try out the coding part on yourself, because this is how it is done in all deep learning models. Now this is the pipeline that we did. Pre-processing, this is very important. Like I said, this is the mean and standard deviation. You can calculate it. Forward activation. Uh, these are the results. We can interpret them easily. Training curve. Yeah. So one very important thing about the confusion matrix that we can interpret is that we can interpret exactly where our model made mistakes. So if you look at this actual right here, you can see that there is this 4 value. Okay. It means that the actual digit was 4, but our model predicted it to be a 9. How many times? 25 times. 25 times in 25 different cases, our model thought that the 4 was a 9. Okay, so this is how you can interpret the mistakes of the model, and this is basically due to the stroke geometry. Basically 9 and 4 look a little bit similar to the model. Okay, so this is acceptable. These kinds of basic ambiguities happen. The same is for the 7 and 2. You see, if the number the inside the image was actually a 2, but the model thought it to be a 7. How many times? 14 times. So that is a huge mistake as well. Okay, so you can interpret these numbers, and this is basically the same confusions that we make sometimes when we see a paper having messy handwriting. We cannot always interpret everything correctly down to the last minute detail. Okay, loss and accuracy curves, simple. Very important thing. Now I'm going to show you why neural networks are not used in everyday problems. And if I give you the reason quickly, the reason is because they are very computationally demanding, very heavy computations. Okay, because I think you can guess this. Why is this? Because from the input layer we were having a lot of interactions. Like a 784 input matrix is interacting with all 28 neurons. How many input weights are those going to be? Then the ReLU, then the layer to get to the output as well, then the softmax, then the backward pass calculation. So it is a computationally like a very heavy model to build. Okay. So to look at the time and space complexity, E is the number of epochs that we are dealing with. So we had 10 epochs here, it is fine. 60,000 images. Okay. What is the input dimension? 784, which was basically 28 into 28 for the pixel images. H is the hidden layer, and our hidden layer had 128 neurons, which we decided logically. And then we train during the backward pass as well per epoch. So in the backward pass, we had got 10 classes again, and then the hidden layer again. So see, this is the total computation that comes out to be. Now, if you calculate this, this is a massive number. 784 into 128. This D into H is the dominant term here. It comes out to be like a 1 lakh weights, 1 lakh parameters. Okay. And then you multiply that by 60,000 and then you multiply that by 10. So this is very massive, massive. Okay. It is manageable on a CPU, but you can see how quickly it is scaling. Like, this is why the decisions for deep learning models matter a lot. You cannot just say, let's train the model for 1,000 epochs or 500 epochs, because it is scaling so quickly, it is soon going to be a bottleneck to handle. Okay. Now the inference complexity, this is what we run in the inference, basically the testing part. So this is still pretty quick, and CPUs can handle this pretty quickly as well. Okay. Now for the space complexity, the model has to store all of the weights that we are having. So we have weights in the input, we have weights in the output, and we have got the bias that I said. So this is the number of parameters for the weight. Bias is going to be equal to the number of neurons, 128. In the output layer, we were having only 10 because we are dealing with 10 classes, and this is the weight. So this is the total parameters that we are having. Okay. You can convert them to kilobyte just for interest sake. This is what it comes out to be, 40 KB, which is very interpretable. So this is for the time, space, and inference complexity. Now, now, we are going to talk about the disadvantages and the failure cases. You see, I could have chosen a different problem to explain and to discuss ANN, because image classification is not ANN strong suit. Okay, which basically brings us to what we'll also do tomorrow on the next day. On tomorrow, we'll be doing what will beat ANN on the image stuff, which basically leads us to discussing what are some of the failure cases for ANN. So there can be many things. The first thing, the simplest thing there is to be, so let me show it to you using an example. So let me go back. So let's say that I take this number here, 5. Okay, and I have an image of 5 right here. See, simple, right? This is simple. Now let's say I make 5 a little different way. I make 5 like this, and I increase my size of the image like this. Now, if I ask you as a human whether both of them are the same, what will you say? Of course, they are the same. The only difference is that here 5 is sort of in the middle and here 5 is in the side. Okay. Or let's say that, let me erase this. Let's say I erase this 5 and, I make it a little bit like this, like a little bit rotated in some angle. Okay. Now I'll ask you, are these two the same? Yes, they are still a 5. But the thing is, the ANN is dumb in this way. The ANN has no awareness about space. It has no awareness about spatial differentiation. It does not know whether spatially two images are different or the same. Now these two should be classified as 5 by the machine learning model that we are building. But ANN will not be able to identify them as different images because it has no idea about space. It will assume them to be different images. Okay, so this is the first disadvantage, spatial ignorance. So it is, ANN is flattening all of the images to a 784 length vector. So it is going to have no idea whether some pixel is different to some other pixel because all it has is 784 numbers in a row. So it cannot really recognize all of the very complicated features that we are dealing with. So it is still very inefficient to learn complicated relationships. Okay. The second is vanishing gradients. Now, like I told you, ReLU solves the vanishing gradient problem predominantly. But if you increase the number of layers, that issue basically comes back. And we also get the dead neuron problem, where some neurons contribute nothing to training, and they are basically dead in the first layer. This increases the issues that we are having. Okay. Overfitting is a big problem. Like I said, the neural network is a very complicated model because there are so many weights and so many parameters. Smaller data sets, mm, neural networks are never recommended on smaller data sets because basic machine learning models are able to solve them. Neural network on a naive data set would definitely be an overkill. Okay. This is the sensitivity to pixel shifts and rotations. Basically, if you shift any number like I showed it to you to the right or left, for the ANN it will be a completely new number. But in actuality, it is the same number. So it has no translation invariance. This is called as image or translation invariance. Basically, uh, when I make the same number in different places inside the image, ANN will not be able to differentiate it in them. It will think that they are different, whereas they are actually the same. Okay. Normalization, again, it is a sensitive parameter in this case. If you don't do this, the raw pixel values will be bad because the some raw pixel values will be very high and they will dominate the training. So we won't, there would be massive issues in doing that. Okay. So these are some of the failure cases. You can read the key takeaways. Okay. So this is it for the first neural network that we built using the ANN. Okay. So it is basically mathematically very superior to anything we have done in machine learning because the idea is very elegant. So you can check out the repo in this case. I don't think I've missed anything. You can look at the diagrams as well in order to visualize it better. Okay. The equations are important. They're not that complicated, which is why they might be asked in interviews as well, and definitely in college exams as well. So I recommend you to practice and check out the equations carefully. If you remember the equations, you will remember the network. The network is just a diagram. If you know what is happening mathematically, you will never forget what is happening conceptually. Okay. And about the activation functions, I will leave another article which has an even deeper explanation about the activation functions, so you can check it out. And I think this is it. So I will leave the link of the repo and the code in the description itself. You are very welcome to check it out. Thank you so much, and I will meet you tomorrow on day 17 with a CNN model. Okay, so the same problem that we have implemented today using something stronger than ANN, something that is made for